this video, we're going to discuss, we're going to derive the general equation for stress within a thick-walled cylinder. So thick-walled cylinders are used typically in applications like in chemical and food processing plants to store gases and liquids under pressure. All right. All right. And so the goal of these systems is to be able to withstand high pressure. Right, typically that high pressure is internal, and they obviously want to avoid catastrophic failure or avoid explosions. Okay, so we want these systems to work and to function and avoid explosions that could damage and hurt other people. Um, so, um, so for a typical thick-walled cylinder, I've drawn a diagram on the right hand, the left hand side here. We have an internal radius and then an external radius, or inner and outer radius, and then within the cylinder there can be a few different types of loads. We can have an internal pressure, which we'll denote with a lowercase p and an I. We can have an external pressure, PO, right, and then we can have a rotational motion, which we can denote with the letter omega. Okay, so those are the three types of loads that we have on our system. Right. So due to these three loads, all right, so due to the external pressure, all right, due to the internal pressure, and due to the rotational motion, if we look at a element within our system, all right, we can look at a small element. This would be a stress element. All right, it will have, so this is our differential radial element. Right, it will have, it will be at some location r. It'll be at some angle theta, and then we'll have the the length of this element will be r d theta, all right, and then the top of the element will be so we have r d theta, and then we have the length of the element in this direction is d theta, and our dr, and then the angle change along the element will be d theta. Okay, so what we'll notice about these types of problems is that they're going to be axisymmetric. All right, so because they're axisymmetric, all right, so all the stresses will be constant with respect to theta. All right, so because of that, there will be no shear strain, and there'll be no shear stress. So both of these terms will be 0. Okay, so what we end up getting for our stress element is we end up getting a tangential stress sigma theta going along the circumference of the circle, and then along the radius we'll have sigma r, and then we'll have sigma r plus any change in that stress, sigma r. Okay, so for both sigma r and sigma theta, all right, there will be only, well, these will both be only functions of r. All right, so they'll only be a function of r, not theta or z. Okay, all right. So our goal for today is we want to find determine what sigma r is and sigma theta are under different loading conditions. Okay, so basically under different cases with external pressure, internal pressure, or rotational motion. So we're going to derive an equation for those different stresses, sigma r and sigma theta. So if we start off, if we sum all of our forces along the radial direction, we can say that that would have to be equal to the mass of our element times our the radial acceleration. So the mass would just be equal to rho times the volume. All right, and then the radial acceleration would be equal to the radius times the rotational velocity squared. All right, so we end up getting this part of our equation. We can repeat the process with our stresses. All right, so we're just going to take our stresses and multiply those by the cross-sectional area. All right, so this is just stress times area. All right, then we minus stress times area. Okay, and what we end up getting, all right, is that if we take these two equations A and B, all right, and we set A equal to equation B, and we set d sigma r dr d theta dz. We say that it's going to be very small, so we're going to say that it's equal to 0. We can get this equation here for our governing equation for how we can relate the radial stresses to our rotational stress and our our tangential stress. So if we're going to make an assumption, we're going to assume that sigma z, or the stress along the z-axis, or coming into like the page, is going to be equal to 0. So we can then use the stress-strain relationships for axisymmetrical problems to determine what would be our strains in the radial and the tangential direction. So we define that the strain in the radial direction would be the ordinary differential of the strain in the rate and of the displacement in the radial direction with respect to the radial direction, which would be equal to this term here, and we can do the same thing for the stress in the tangential direction. If we multiply both sides of this equation here by r, we can then take the derivative of ur with respect to r. So, and if we do that, what we end up getting is we have this equation here. Okay, what you'll notice is that both this term here and this term here are both equal to du of r with respect to dr. So we can set both of those equal. So we can set equation 2 and equation 4 equal to each other. All right, and we'll end up with this equation here. All right, so we can rearrange. If we go back to this term here, if we look at equation 5.81, we can rearrange in terms of just sigma theta. So we can just move sigma theta to the other side and bring this term over. All right. If we do that, we'll get the following equation on the next page here for sigma theta. All right. So now we should be 8, and then we can take the derivative of this with respect to r. Okay. Now we're left with this equation here. All right. Now we can plug in equation 6 and equation 7 into equation 5, and we do all that, we'll end up with an ordinary differential equation that is just in terms of sigma r. All right, so it's all in terms of one variable. All right, and this is going to be our governing equation for thick-walled cylinders. All right, so we're going to use this equation to determine the stress and the strain. The two stresses. So we'll use this to determine sigma r, and then we know that once we have sigma r, we should then be able to find sigma theta. All right. So in short, the major thing is we've established some relationships between sigma theta and sigma r, and now we have an ordinary differential equation that we can use to determine a solution for sigma r, and we can then find sigma theta.